Hey everyone, I'm Pratik Sharma, team head of Avishkar Hyperloop, and I'm thrilled to welcome you to this special collaboration between Avishkar and GSC for an exciting lecture series presented by Global Hyperloop Competition. But first, let me tell you a bit about who we are. Avishkar Hyperloop is a passionate team of students from IIT Madras, where Avishkar means inventing, and that's exactly what we do. We dive deep into research and development of Hyperloop technology and participate in competition and conferences all around the globe. Our journey began in 2013 with the dream of competing in the SpaceX Hyperloop competition, and over time, our vision has evolved. And now we are committed to develop the world's first and most economical Hyperloop system. And for that, our efforts have not gone unnoticed. We have received support and praise from some remarkable figures, including our Honorable Prime Minister Narendra Modi ji, Railway Minister Ashwini Vaishnav ji, Finance Minister Nirmala Sitharaman ji. We made history by becoming the only Asian team to qualify for a SpaceX competition. However, when the SpaceX competition ended, a new opportunity emerged on the European stage, the European Hyperloop Week, and we have consistently been in the top 5 since its inception. Now, let's delve into the heart of the matter. What exactly is the Hyperloop? Contrary to the popular belief, Elon Musk is not the sole brain behind the Hyperloop. The concept dates back to 1914 when Dr. Boris Petrovich Winberg introduced the idea in his book named Motion Without Friction, calling it the Vectrain. Fast forward to 2013, and Elon Musk revived the concept in his white paper using the term Hyperloop. Now, let's dive into the technical stuff. For the better understanding, I have divided the Hyperloop into different components. Here we have on-board system and off-board system. In on-board category, we have levitation, propulsion, electrical, and mechanical system. First, we have levitation. Main goal of levitation is to produce a lift force to levitate the pod. To eliminate the losses brought on by friction force and other restriction imposed by traditional wheels in high-speed transportation. For producing lift force, we have two main ways. One is by using EDS and other by using EMS, where EDS stands for electrodynamic suspension, which makes use of repulsive force of magnet. EDS is being widely used in maglifts, but the issue with EDS is that it requires a high relative velocity, whereas EMS electromagnetic suspension makes use of attractive force of magnet and can work at all speeds. Therefore, we are using EMS on our part. Implementation of EMS depends on its hardware and software, where hardware consists of ferromagnetic core and copper coil, and they are combined in such a way that when DC current is passed in coil, it generates and concentrates magnetic flux in the ferromagnetic core, results in producing lift force. Now let's focus on how to control EMS. For controlling, we use PID control, where the feedback to the levitation control unit is received from the gap sensor and compared with the reference air gap results in generating PWM signal. Accordingly, then the control unit sends output PWM signal from the current loop to the DC-DC converter, which supplies the required current to the EMS coil. This covers the basic of the levitation. This video shows the working of EMS with the control loop. Moving forward, we have propulsion system. Goal of propulsion system is to accelerate the pod without making any contact. And for that, we are using linear induction motor. The working of LIM is similar to the working of induction motor. So in an induction motor, we have a stator and a rotor. And if we cut the rotor and unroll it, then we get a linear induction motor. As shown in the picture, now, the third component is the electrical system. Main responsibility of this system is to safely deliver power to all components of the pod. For that, we have two battery packs, primary and secondary, where major of the power originates from primary battery pack to power propulsion and levitation system. And power from secondary battery pack is fed to the embedded system, where embedded system handles the coordination and synchronization between different subsystems using PCB and sensor, and it also adds a layer of safety. Lastly, the mechanical system. Main task of mechanical subsystem is to design a lightweight yet structurally robust chassis. Suspension to dampen the impact which comes due to the transition from levitating state to on-wheel state. And to design aerodynamic cell and to design braking circuit with appropriate factor of safety. When all on-board components are combined, we get a running pod as can be seen in the video. Now, for off-pod, we have infrastructure which will be explained by Pranav.
Hello everyone, I am Pranav Sakure, Infrastructure Lead at Avishkar Hyperloop. Today I want to take you on a journey into the world of Hyperloop infrastructure and share with you why we embarked on this journey. Infrastructure is the backbone of transportation industry, which involves a significant capital investment. To put it in perspective, if you want to travel just 1 kilometer on a regular train, the cost of a engine is mere 2 crores, but setting up 1 kilometer of rail, that's 5 to 10 crores, almost 2.5 times the cost of the engine for just 1 kilometer. Now imagine ramping up the speed to 320 km per hour. The high-speed train infrastructure cost will be around 100 to 140 crores, while the engine would be still 10 crores. So where is the hurdle? The major infrastructure cost, and this challenge is not different in case of Hyperloop. That's why we started working in the infrastructure field to make it more economical and sustainable. Infrastructure of the Hyperloop is made up of four parts: vacuum tube, track, civil structures, and vacuum systems. Let's take a closer look at the cost analysis of our Hyperloop prototype testing facility. As we can see, out of the total 9.5 crores for the project, the infrastructure cost accounts for 8.5 crores, which is 90% of the whole project, and the vacuum tube only accounts for 40% of the infrastructure part. Thus, the reduction in the cost of the tube will directly relate to the reduction in the total cost of the project. So that's why we started working on an entirely new novel approach to design the vacuum tube to reduce the cost of the tube. Our methodology to design the tube has been divided into five parts: ASME approximation, iterative methods, asymptotic analysis, which is followed by cost analysis and experimental validation. So let's start with the first part. Hyperloop's tube design should be economical, scalable, and most important, safe for the passengers who will travel inside the tube. The most important parameter that would decide the scalability of the Hyperloop tube is the thickness of the tube. A vacuum tube could either fail due to yielding or buckling, which would be based upon the slenderness ratio. A slenderness ratio is the ratio of the diameter and the radius of the tube. If the slenderness ratio is less than 80, then it would fail by yielding, and if the slenderness ratio is more than 80, then it would fail by buckling. But if the failure is due to yielding, then that will lead to high thickness and also high factor of safety, which is good, but we will not be able to get economical and scalable Hyperloop tube. But if the failure is due to buckling, then we will be able to reduce the cost as well as there will be reduction in the FOS. And optimizing the cost, and the factor of safety is the most important part. So this is the process of designing the Hyperloop tube through the standards. We have followed ASME BPVC code for designing thin pleasure vessels. From the code, we have arrived at the parameter of 2-meter diameter, thickness of the stiffener 6 mm, and length between the stiffeners 1700 mm. But when this design was checked with our computational methodology, it resulted in a very high factor of safety. So we performed an extensive iterative analysis to find out the design which would be economical and should have an optimum factor of safety between 1.5 and 2. As a result, we finalized two designs with interstiffener spacing 2200 mm and 3000 mm based on the cost and factor of safety. This is our computational methodology which we used in iterative simulation as well as in the asymptotic analysis. Asymptotic analysis will be discussed more in the following presentation. It comprises of static structural simulation, eigenvalue buckling analysis, and nonlinear buckling analysis. Nonlinear buckling analysis will take into account both material and geometrical nonlinearity. After rigorous iterative simulation, we performed this asymptotic analysis to identify a design which would be capable of sustaining reduced factor of safety with the increase in the length. And through this, we are able to get final factor of safety which would be unaltered with further increase in the length. As per the final FOS, we selected 2200 mm interstiffener spacing model, which was economical compared to 1700 mm model and was having optimum factor of safety between 1.5 and 2. And our to ensure robustness of our computational method, we conducted two destructive tests, one for global buckling and another for local buckling. The results, these are the videos of both global and local buckling destructive testing, validating our methodology to be 95% accurate in predicting the buckling pressure and FOS of the tubes. Through this rigorous process, we have achieved an incredible 46% reduction in the tube cost compared to the traditional approach from the codes.
Pranav have explained how we managed to reduce the thickness and cut the cost of the tube, but then the question arises as to why others cannot do that. The answer to that lies in the topology of the track, and for that we need to understand the requirement of the track. So let's proceed. In 2013, when Hyperloop was proposed by Elon Musk, he proposed I-beams to be used as a track. But as the models were tested, a few issues arose. If you want to use I-beam, then your pod center of mass should lie on the middle of the track. Otherwise, it will cause stability issues. And also, width of the pod cannot exceed certain limits. Otherwise, it will cause too much stress on the middle part of the beam. Hence, for scalability perspective, I-beam is not the best choice. So, how to design track? To design track, we need to understand the requirement of track, that is to support levitation and propulsion. Where for levitation, EMS requires paramagnetic material such as mild steel, and then for propulsion, LIM requires paramagnetic material like aluminum. Now, as can be seen in the picture, we have a middle section made up of aluminum to support LIM, and on side we have inverted F mild steel track which supports the levitation and takes all load from pod. So we have gathered the enough knowledge to answer the question that I raised earlier. To mount track inside the tube, there are two ways to do that. One is to mount the tube on top half of the tube, also known as hanging track. As shown in the picture, if we go with hanging track and mount it along the length of the tube, then all the loads from the track and pod will directly be transferred on the tube. Hence, in this case, the thickness of the tube should be more to bear those loads, which will directly increase the cost. Another way of mounting track is that if we mount track along the length of the bottom half of the tube. In this scenario, all the loads from the track and pod will directly land on the tube, and the same reasoning applies here. Hence, there is an increase in thickness and cost. Now, coming to how we are managing to reduce thickness. We are installing a track on an inner block which is directly placed over the pylon in such a way that all the loads from the track are directly transferred to the pillars and not to the tubes. We have been granted patent for these two innovations, reducing the thickness of the tube and assembling the tube and track. Lastly, I am proud to announce that we will be inaugurating the world's first student-run Hyperloop testing facility. This facility boasts a 400-meter vacuum tube and track, entirely designed by our dedicated team of students. Thank you.